with our online class. I'm going to share with you application of second order differential equation, which is a spring mass system. Okay, everybody, are you ready with me? And then don't forget to sign the attendance through UFuture. Okay. During my presentation, if you have any problem, please do ask question. Okay, the main objective for today's online learning is first, we are going to translate or formulate the vibration of spring mass system into mathematical model md square x dt square plus beta dx dt plus kx equal to f of t. Okay, I'll explain later about this equation. Then we are going to find the equation which describes the motion or displacement of the object at time t. Sorry. Then we are going to identify the types of motion and compute the maximum displacement, period, and frequency. Okay, before we start the problems of solving spring mass system, let me introduce you a little bit about what does spring mass system mean. Okay, let's say we have a spring with a natural length of L meters. I'm going to use metric system here, the length in meters. And then we hang the spring vertically on the rigid support, such as ceiling. Okay, here is the rigid support. After that, we hang or attach an object with a mass m kilogram. This will cause the spring to stretch by s meters. The object will be at equilibrium position, static here. So this level is known as equilibrium position. Okay, to set a spring in motion, we may pull down the spring or the object below the equilibrium position and release the object, and the spring will be vibrates or moving up and down. Okay, we have to stop for a while because there is a technical problem. Okay, let's continue. Okay, as I mentioned before, we will set the spring in motion, whether it is from equilibrium position or from a certain distance above the equilibrium position or below the equilibrium position. Okay, our main goal is to find the displacement of object at time t. So from the displacement, from the equilibrium position. So at equilibrium position, we said that the distance is 0 because the object is on the equilibrium position. So here we use x of t equal to 0. Okay, above here, we use x of t, which is the distance of the object from the equilibrium position, is less than 0. And down here, below equilibrium position, we use the displacement of object as less than 0. Greater than 0. Greater than 0 because we follow the gravity. Okay, at this equilibrium position, the two forces involved, they are balancing each other. One of them is known as restoring force. Restoring force. Okay, according to Hooke's law, the restoring force is equivalent to K times S. S is the elongation or amount of stretch here. K is the spring constant. This is the spring constant. It is the stiffness of the spring. The unit is in Newton per meter. And then another force due to the gravity, we label it W for weight, which is equal to M times the gravity. M is the mass, the unit is in kilogram, while the gravity used here is 9.8 meter per second square. So at this position, the weight is equal to the force due to the restoring force from the spring. So we may write it as mg equal to k times s. Or we may write it as mg minus ks equal to 0. Laju sangat. Okay, let's have a look on this statement. At t equal to t second, the object is 3 meters above the equilibrium position with a downward velocity of 2 meter per second. Okay, here if we see the distance is 3 meters above the equilibrium position, so we may write x of 3 equal, x of 3 seconds, 3 seconds equal to minus 3 meters. And then another the velocity is denoted as x prime of t. Okay, we use x of t as the distance. X prime of t is the rate of change in distance with respect to time t. This is the velocity, or dx over dt. So we use upward velocity. If it is upward velocity, we use the value less than 0, while for downward velocity, we use x prime of t greater than 0. Okay, so here, if the statement a downward velocity of 2 meter per second, then we write it x prime of t because of the velocity. And then here is the direction, downward. We use positive 2 meter per second. You have to understand the concept of direction of the object and also the direction of the velocity. Okay. Another forces acting on the spring or the system of spring is damping force. Damping force is the resistance from air resistance or any surrounding medium. It causes the vibration of the spring to slow down and maybe stop later. The damping force is given by beta dx dt. Beta is the damping constant. Damping constant times dx dt is the instantaneous velocity. Then another force acting on the system is known as external force, except the three forces discussed or known as driven motion. It may come from the movement of the rigid support where we hang the spring. So we label it as F of t. Using the Newton's second law, the net force is given by the summation of the four forces, which is forces due to gravity, which is weight, m times g, plus the restoring force from the spring, Fs, which is minus k times s plus x. We use the negative sign here because its direction is opposite the direction of the movement of the spring. Same thing goes to damping force. We use negative sign here because of the opposite direction of the movement of the spring. And finally, the external force. And then this equation can be simplified as m d square x dt square plus beta dx dt plus kx equal to f of t. Because of here, mg minus ks is equal to 0 from the equation before. And then a is the acceleration. So we use x of t as the distance at time t, x prime of t as the velocity, and x double prime of t as the acceleration. In bahasa, we call it pecutan. Or we may write it d square x dt square. Okay. M is the mass in kilogram. It is a constant. Beta is a damping force, which is also a constant. Spring force is also a constant. And then we have external force. So this equation is similar to the one that we learned in the previous chapter. Remember this? A d square y dx square plus b dy dx plus c equal to f of t. So we will solve this equation using the same way as we learned in chapter 4. Next, we move to types of motion. One of them is free undamped motion, or known as simple harmonic motion. In this case, there is no external force, no external force, and also no damping force. No damping force. So the differential equation is md square x dt square plus kx equal to 0 because of no external force. And then we have another type of motion known as free damp motion, where here is only damping force, no external force. Okay, meaning here the external force is 0. Beta dx dt is the damping force. There has a damping force in the system. The last one is the driven motion or external force, where f of t is not 0. For the free damp motion, we classify it into 3 types. Under damp motion, where b square minus 4mk equal to greater than 0, we find there are 2 different real roots for this question. And then another is critically damped motion, repeated root for this motion. And then we have under damped motion, which b square minus 4mk is negative values. Okay. Next, this is the summary of the type of motion as I mentioned before, and the general solution that will the general solution for each type. We will discuss this in the problem 1 below. Okay, let's move to the free undamped motion. Example 1. Okay, let's read the problem together. An object weighing 19.6 Newton attached to a lower end of a spring stretches it by 2.5 meters. Okay, meaning here we have the spring. Down here is a mass with the force given is 19.6 Newton. This is the force or weight. And then the elongation or amount of stretch here, which is S, is equal to 2.45 meters. The object is released or start in motion from equilibrium position. So let's say this is the equilibrium position. At this equilibrium position, the distance of object to this equilibrium position is 0 meter. Initially, the time we take as 0 at t equal to 0. And what else is given in the question? Upward velocity. With an upward velocity of 3 meters per second. So here, the velocity, which is x prime of 0, which is negative or positive? Are you with me? Upward velocity, we use negative 3 meter per second. Okay, in the question, there is no damping force and external force. Therefore, the model will be mx double prime plus kx equal to 0. Damping force 0, external force 0. So we have to find the mass in kilogram. Also the K, which is the spring constant. Okay, A, we will formulate an initial value problem that models the system. So we have F equal to 19.6 Newton and S equal to 2.45 meters. Initial condition is x of 0 equal to 0. And the velocity is minus 3. Okay, let's calculate the value of m. And the value of k. Okay, we will calculate the value of k by using force equal to ks according to Hooke's law. F is 19.6 meters, 19.6 Newton equal to k times 2.45, the value of S. Make sure the value of S is in meters. If the question is in centimeters, then we have to convert the length in meters. Okay, 19.6 divided by 2.45, we get k equal to 8. This is Newton per meter. And then we calculate the value of m using W equal to F, which is mg equal to 19.6. And we use gravity equal to 9.8 meter per second square. Solving for m, we get 2 kilogram. Then substitute the m and the k in the differential equation. This is the initial condition. X of 0 equal to 0. X prime of 0 equal to not minus 16. Minus 3. Is it minus 3? Yeah, minus 3. Not minus 60. Minus 3. Okay, this is the differential equation that represent the spring mass system. The answer for part A. Any problem with that? Any question?
No, madam.
So you have to remember two basic formula here. F equal to Ks. Weight is equal to mg. Next is to find the distance of object or displacement of object at time t. So we need to solve this differential equation. Remember, on the right hand side, the equation is equal to 0. This is a non or homogeneous? Homogeneous differential equation. So first, we have to find the characteristic equation or auxiliary equation by replacing d square x dt square with d square. Before this, we use d square y dx square with m square. I'm not going to use m because of m is used for the mass. So use different variable. And dx dt with variable d and x with d to the power of 0, which is 1. So here d square plus 4 times 1 equal to 0. We get d square plus 4 times 1 equal to 0. So for d square is minus 4 and d is plus minus square root negative 4. If we have square root negative number, then they will be a complex number. So we solve it this way, plus minus square root 4 times minus 1, which is plus minus square root 4, square root minus 1, which is equivalent to plus minus 2i. For a complex number, if the roots is alpha plus minus beta I, then the solution, the general solution will be e to the power of alpha t times C1 cos beta t plus C2 sin beta t. So here, d equal to plus minus 2i, which means alpha is here. The value of alpha is 0, beta is 2. That's why we get the general solution x of t equal to e to the power of 0, which is 1 times C1 cos 2t, beta is 2, and C1 times cos 2t plus C2 sin 2t. Okay, substitute beta with the value of 2. Actually, we solve same as the one that we did in chapter 4. Next, we have to find C1 and C2. So we apply the initial condition given. First is x of 0 equal to 0. Substitute t with 0. X of 0 equal to cos C1 cos 2 times 0 plus C2 sin 2 times 0. Cos 0 is 1. Sin 0 is 0. So we get x of 0 equal to C1 plus 0. X of 0 is given is 0. C1 equal to 0. That's why we get here. Another condition is the velocity at t0 equal to minus 3. So here we don't have the function x prime of t yet. Therefore, we need to differentiate x of t. C1 cos 2t plus C2 sin 2t. Differentiate this function, we will get differentiate cos 2t is minus 2 sin 2t. So minus 2c1 sin 2t. And then differentiate sin 2t is 2 cos 2t times c2. So we get 2c2 cos 2t. Then substitute t equal to 0. inside here. Then we get sine 0 is 0, cos 0 is 1. Cos 0 is 1, sine 0 is 0. Then substitute the velocity minus 3 equal to 2c2. Then solve for c2, we get minus 3/2. Then for this part, conclude the answer. Which is the equation of the motion at time t is x of t equal to minus 3/2 sine 2t. Okay, the next part is to find the position of the object at time t 2 seconds. So just substitute t equal to 2. So get minus 3/2 sine 2 times 2. Here, substitute t equal to 2. We get 1.1352 meters. Remember to use the calculator in mode radian. Then you get this answer. Positive 1.1352. It means that at t equal to 2 seconds, the object is below the equilibrium position by 1.1352 meters. Meaning here, this is the spring, the object, and this is the equilibrium position. The distance here is 1.1352 meters below the equilibrium position. So in general, if the system has no damping force and no external force, the differential equation is md square x over dt square plus kx equal to 0. And then we get the characteristic equation, d square plus k over m equal to 0. To simplify the equation, we substitute k over m with omega square. So we get d equal to plus minus omega times I. Then the general solution would be x of t equal to c1 cos omega t plus c2 sin omega t. From this equation, we may calculate the what we call it period, frequency, and amplitude. The period of the motion indicates the times in seconds for mesh to execute one circle of motion, and it is given by 2 pi over omega. The unit is in seconds. And the frequency is the number of cycles completed in 1 second. So frequency is equal to 1 over t or omega over 2 pi. And finally, the amplitude, which is the maximum displacement. A equal to square root of C1 square plus C2 square. Okay, for example, x of t equal to minus 1.5 sine t, C1 will be, let's compare with this equation. C1 will be 0. Okay, no cos here. So C2 is the coefficient of sine omega t. So C2 is minus 1.5. So the period would be 2 pi over omega. So in this case, omega is equal to, here omega, so the value here is 2. So omega is 2. So substitute here, 2. 2 pi over 2, we get pi, or 3.14 seconds. So it takes about 3.14 seconds to complete one cycle. One cycle means from here we use two successive maximum point for this graph. From this maximum to this maximum, the time will be 3.14 seconds. Or we may use the two successive two successive minimum point, which is from here to here. So it takes about 3.14 seconds. Okay, the next part is the frequency, which is 1 over t. We get omega over 2 pi. Substitute the value of omega, which is 2 divided by 2 pi. We get 1 over pi circle per minute. Sorry, per second. Per second, not per minute. Okay, the amplitude here, meaning the highest distance here, we calculate it by using this formula. A equal to square root of C1 square plus C2 square. Substitute the value of C1 and C2. Then we get 1.5 meters. So here the amplitude, 1.5 meters here. Also the same here. Okay, this is the graph of simple harmonic motion. Meaning here, the vibration of the spring will continue forever. Non-stop moving for simple harmonic motion. Any problem with that? Any question? Before we move to another example. Okay, we go to example 2. A mass weighing 9.8 stretches the spring 0.2 meter. So meaning here, force. Here is the force. 0.2 is the amount of stretch, which is 0.2 meters. At t equal to 0, the mass is released from 0.25 meters below the equilibrium position with an upward velocity of 4 meters per second. So if we draw the spring like this. Okay, this is the original spring. And then we attach an object at the lower end of a spring. The spring will be at equilibrium position. And then at t equal to 0, we will set the spring in motion. It start where? Here. 0.25 below the equilibrium position. This is the equilibrium position. So below the equilibrium position, somewhere here lah. So this is the distance. We write it at time 0. The distance is equal to positive or negative? Hello?
Negative.
Are you with me? Positive 0.25 meters because we use the direction of gravity as the positive value of the distance. Another information is the upward velocity. Okay. We have a spring with the object. Pull down the spring about 0.25 meters and release the object. Then the spring will oscillate up and down. It will move. It will swing up and down. It will vibrate up and down. So we are interested to find the distance of the object at time t. Okay, part A, determine the equation of the motion. The equation of the motion meaning the equation of the displacement of the object. Same thing at time t. When we read the question, there is no damping force or external force given, meaning that the spring mass system is in type of free undamped motion or simple harmonic motion. Therefore, the equation should be md square x over dt square plus kx equal to 0. We have to calculate the mass m and also the spring constant. Substitute this value, then we solve the differential equation. Okay, same thing as the first example. We use W equal to mg to get the value of m. So in this case, m equal to 1 kilogram. Then this is not m, this is k. So k we get 49. F equal to k times s. S given here is 0.2 meters. And then this is the condition. So we get the differential equation that represents the system of spring mass. D square x dt square plus 49x equal to 0. X of 0 equal to 0.25 and x prime of 0 equal to minus 0.4. Do you understand how to find m, how to find k, how to set these conditions? Any problem with that? No problem. Okay, good. No problem, madam. That's good. Okay, solve the equation. Find the characteristic equation. Solve for D. So we get D equal to plus minus 7i. The general solution is C1 cos 70 plus C2 sin 70. So I move the solution. apply the initial condition to get the constant C1 and C2. Substitute the first condition, T0. So we get C1 equal to 0.25 and get x prime of t by differentiating x of t. Substitute t equal to 0 and then solve for another constant, which is C2. Then conclude the general solution. We get x of t equal to 0.25 cos 2t minus 0.0571 sin 2t. Next is to find the amplitude. The formula is square root C1 square plus C2 square. So C1 here is 0.25. C2 is the coefficient of sin 2t, which is equal to 0.0571. Substitute these two values, then get the amplitude, 0.256 meters. This is the maximum distance of the object from the equilibrium position. The period is 2 pi divided by omega. So the value of omega here, 7. Substitute omega with 7, then we get the period, 2 pi over 7 seconds. It's the time to complete one cycle. Then the last part is frequency, 1 over t. Omega divided by 2 pi. So we get 7 over 2 pi cycles. The unit is cycles in a second, not in a minute. Okay, we have 1 more hour left. Before we continue with another type of motion, is there any problem with the 2 examples discussed before? No, madam?
Madam. Madam,
Ya,
madam.
ya.
Nak tanya kan dekat example 2 tu, kan soalan dia, kan outward velocity tu, nilai dia jadi positif. Kalau negatif macam mana, madam?
Kalau negatif, upward velocity.
Kalau positif outward velocity
Positif downward velocity.
Oh, so kalau outward dia negatif lah, madam.
Yeah, opposite the direction, opposite the motion. Opposite the, yalah, motion.
Nice. Okay, madam. Thank you.
Yeah. Let me show you. Mana the example tadi? Yeah, we have to alert with the sign of the values of distance and also the velocity. Okay, if it is stated like, let me give you some example. The object is 4 meters above, say at t equal to 0. The object is 4 meters above the equilibrium position with a downward velocity of 1 meter per second. So we write it as x of t. X is the distance. So this is the distance. 4 meters is the distance. So we write it x of 0, t is 0. Equal to, tak boleh tulis ke ni? Okay. Sorry, problem with the pen. 4 meter, x of 0. Sorry, 4 or minus 4? Above, minus 4. Minus 4. I don't know what happened to this pen. Minus 4. It's stated here below the equilibrium position, then positive 4. That is the distance. And then another part is the velocity. Here, downward velocity. So we use the velocity is x prime at t0. So put the 0 inside. This is the time 0. And then downward velocity positive 1 meter per second. Is it okay with that?
Okay, madam.
Okay, we move to the second types of motion known as freedom motion. Here there's a damping force, but no external force. The external force is equal to 0. And here the damping force is not 0. B dx dt is not 0. Still, we get the homogeneous differential equation. The way to solve homogeneous differential equation, we find the characteristic equation. Then we get the solution according to the roots of the solution. If the roots are two different real roots, then we get x of t equal to c1 e d1t plus c2 e d2t. Yeah. If we get repeated roots, then the general solution would be C1 E dt plus C2 times T E dt. And then if we have complex root, this is the solution. X of T E alpha T times C1 cos beta T plus C2 sin beta T. And then we have three types of freedom motion. One is over-damped motion, over-damped free motion. Second is critically damped motion. Third is under-damped free motion. So we may check the type of motion by checking the value of b square minus 4 mk. From here, b square, beta square, minus 4, the value of m, the value of constant. If it is greater than 0, we will get two different real roots. If the value b square minus 4mk is 0, we will get repeated root. And then last one, if we get less than 0, we will get complex root. Okay, we move to the third example. The new thing for this problem is only to find the value of mass in kilogram, to find the spring constant, and to identify the value of damping force. In solving the problem, we use the way we solve homogeneous differential equation in chapter 4. Okay, let's read together example 3. A 2 kilogram mass is attached to a spring with a spring constant 24 Newton per minute. Newton meter. 24 Newton per meter, not per minute. Newton per minute. So in this problem, we don't have to calculate the mass because the mass is already given in kilogram. So M is 2 kilogram. Spring constant is also given. So K equal to 24 Newton per meter. And then another information is that the system is immersed in a medium imparting a damping force equal to 16 times the instantaneous velocity. Meaning here, the damping force given P dx dt, beta dx dt equal to 16. Instantaneous velocity is the velocity dx dt. No external force. So, the differential equation that represent this spring mass system is m x double prime plus beta x prime plus kx equal to 0. Substitute the value of m, substitute the value of beta, and also k. Okay. For the initial condition, let's look at this sentence. Find the equation of the motion. We have to find x of t. This is the condition given. If it is released from rest, okay, another vocabulary here, rest. Rest meaning not moving. Kalau dalam bahasa kita panggil pegun, tak bergerak. Meaning the velocity x times 0 is 0. Okay, the object is not in moving. The object is at rest. Meaning x prime of 0 is equal to 0. At a point 80 cm above the equilibrium. So we write it as x of 0. This is the distance. So x of 0 equal to positive or negative 80 cm. I'm asking, is it positive 80 cm or negative 80 cm?
Negative.
Yeah, you are correct. Alhamdulillah. Negative 80 cm. But we need to convert the distance into meters. So how to convert cm into meters? 1 meter is equivalent to 100 cm. So we divide by 80 minus 80 divided by 100. We get minus 0.8 meters. So let's have a look on the differential equations. We are given the mass, damping coefficient, spring constant. The initial condition, x of 0 equals to 0.8 meter and x prime of 0 equal to 0. Because here at rest, no motion. Meaning velocity is 0. Then we solve the equation. Find the characteristic equation by substituting d square to d square x dt square. Substitute d to dx dt and d to the power of 0 or 1 to x. This is the characteristic equation. 2d square plus 16d plus 24 equal to 0. Simplify this equation, d square plus 8d plus 12 equal to 0. So for d, okay, factorize this equation or you may use the quadratic formula. D equal to minus b plus minus square root b square minus 4ac divided by 2a. So we get d equal to minus 6 and minus 2. So here we get two different real roots. Therefore, the general solution would be x of t equal to C1 E D1 T plus C2 E D2 T. Substitute D1 and D2. Minus 6 here and minus 2 here. Okay, D1 minus 6, D2 minus 2. Next, we have to find the values of C1 and C2. To get these values, we apply the initial conditions given, which is x of 0 equal to minus 0.8. So substitute here, t is 0, t1 e to the power of 0. C1 e to the power of 0 is 1 plus C2 e to the power of 0, which is 1. X prime of 0 is minus 0.8. So we get C1 plus 2, C2, C1 plus C2 equal to minus 0.8. So we cannot solve for C1 and C2 yet. We need to have another equation. Alright. The next condition is x prime of 0 equal to 0. We don't have x prime of t yet. Therefore, we need to differentiate x of t to get x prime of t. Minus 6c1 e minus 6t minus 262 e minus 2t. Remember, we get x of t is c1 e minus 6t plus c2 e minus 2t. So x prime of t, differentiate both sides. Here c1 e minus 6t, differentiate minus 60, we get minus 6. So here also, we get C2 E minus 2T, differentiate minus 2T is minus 2. That's why we get this. Then substitute T0. So we get another equation. Solve these two equations simultaneously. So we get C1 equal to 0.4 and C2 equal to minus 1.2. So here I try to eliminate C2 by multiplying equation 1 by 2 and then adding equation 1 and 3. You may use substitution method also to get C1 and C2. Then finally we get the equation of the motion x of t equal to 0.4 e to the power of minus t minus 1.2 e to the power of 2t. And then the type of motion here, over damped free motion. Because we have two different real roots, or we check b square minus 4ac greater than 0. Okay, if we sketch the graph, we get the motion like this. No up and down swing. So the graph is moving towards equilibrium position and then stop. Start here, 0.8, because x of 0 equal to minus 0.8. This is the distance, x of t. Here 0, positive here, up here is positive and down here is negative. This is the graph. Different from the harmonic motion. The first example, we get the swing is like this, up and down, up and down. It will swing forever. But this one, the motion will stop at its equilibrium position. Because of what? Because of the damping force that will slow the motion of the spring and finally stop the motion at equilibrium position. Okay, move to another example. Please read the question. 1 kilogram mass stretches a spring 20 centimeters. So here we need to change the unit. 1 kilogram here is the mass given. The spring is attached to a dashboard that impart a damping force. The value of damping force is given, which is equivalent to 14 times the instantaneous velocity. And the condition given, C, where the spring is initially released. It's released from equilibrium position with an upward velocity of 10 meters per second. Okay, M is 1 kilogram. Damping constant 14. Convert the amount of stretch as 20 divided by 100. So we get 0.2 meters. And then we don't have the spring constant. At equilibrium position, the weight is equal to the force due to the restoring force from the spring. Weight is M times G. F is K times S. Substitute the value of gravity. And the value of K, solve for K. We get K equal to 49 Newton per meter. This is the spring constant. How about the initial condition given? What is the value of x of 0? What is the value of x prime of 0? Anybody?
X0 equals to -10.
X0, x represent the distance. -10 is the velocity. Velocity x prime.
X0 equals to 20.
Where do we get 20?
Stretch a spring 20 cm.
No, that's not
No.
right.
Oh.
Okay, let me explain again. Thank you for responding. At least I know that some of you don't understand the condition given. So, the problem is like this. Okay, we have a spring. Please be with me. Focus, yeah? Okay, this is original length. Sorry, original length here without the mesh. Okay, we attach an object with m kilogram. So, the object will stop here. It's not in moving yet. We not release the moving yet. So here, x of 0, we say equal to 0. Because the object is on the equilibrium position, the distance of the object to this line is 0. It's on the line. Okay. Now, we are going to set the spring in motion. So, at t equal to 0, where? Read this. The equation, the mass is released from equilibrium. Start in motion at equilibrium. Here. Start in motion here. So meaning x of 0 is what? Is 0. Because the object is on the equilibrium position. The distance of the object to this line is 0. Okay, different from the previous example. Yeah, you really need to understand the problems given before you are able to set the right differential equation that represent the spring mass system. Okay, here. Go for let's have a look on the previous example. The condition. The solution. Wait, What is the first example? Here. The object is released, same thing here, at equilibrium position. So the distance of the object at time 0 is 0 because the object is on the equilibrium position. And here upward velocity. The velocity we represent it as x prime of 0. 0 is the time, the initial time. Equal to upward velocity, direction upward. So the sign is negative 3 meter per second. And then you see here, meter per second is the velocity. The distance is in meter. The velocity is in meter per second. If you see the unit of the value given, then you know that is the velocity or the distance or displacement. Here also. See the condition. The mass is released from 0.25 meters below the equilibrium position. T0 is the initial time to set the object in motion. So we take T equal to 0. So in this case, the object is 0.25 meter below. This is the equilibrium position. So meaning the object is pulled down and released. So the distance is 0.25 meters positive. While the velocity, the initial velocity is upward velocity. This is the velocity. So we will use negative sign or positive sign. Upward. So negative 0.4 meter per second. For this part, 20 cm is not the initial displacement. It is the amount of stretch. Like this. We have a spring. Then we attach a mass of 1 kilogram. Dia akan kat sini lah. It will stop at equilibrium position. This is equilibrium position. Not in motion yet. Okay, this is the original length. This is the amount of stretch, 20 cm. You imagine you have a spring, hang an object at the lower end of the spring will stretch. The spring will stretch by how much? 20 cm. So this is the S, amount of stretch. Not the distance of object at time t equal to 0. Okay, this is the S, which we will use to calculate the value of K. K is the spring constant. Okay, back to this problem. The initial velocity, upward velocity of 10 meter per second. So here the velocity minus?
Minus 10.
Yeah, that's right, minus 10. How about x of 0? At equilibrium position?
0.
0. At last you get it, yeah? Then substitute the value of m, beta, and k. Initial condition, because it starts moving at equilibrium position. That's why we write it as x of 0 equal to 0. Starts moving. Then solve the differential equation. Get the characteristic equation. We get the repeated root. So the equation is C1 e minus 70 C2 times t e to the power minus 70. Apply the initial condition. We have x0 equal to 0, x prime of 0 equal to minus 10. Substitute t equal to 0 in x of t and get the velocity by differentiating x of t. Okay, to differentiate the first part, we just differentiate directly. But on the second term here, we have to use product rule. This is a product of two functions. C2t times e to the power of minus 70. So this is u, C2t, v is e to the power of minus t. And use product rule. If we differentiate function, the product of two functions, u times v. So the formula is u v prime plus u v u prime. U v u prime. So take it u as C2t, v is e minus 70, u prime is C2, and then v prime is minus 7, e minus 70. Substitute in this formula, we get this part. Then substitute the condition given, x prime of 0 equal to minus 10. So we get C1 equal to 0, C2 equal to minus 10. Finally, the equation of the motion at time t is minus 10t e to the power of minus 70. If we want to calculate the displacement of object at t equal to 3 seconds, Then substitute t with 3.
Terbuka.
Sorry. This is the equation of the motion. Any problem with example 4?
No, madam.
Yeah?
No, madam.
No, madam. Okay. Last example. Okay, I won't show the solution yet. Please read the example 5. I want to ask you what are the info given. First sentence. A mass weighing 4.9 Newton is attached to a 5-meter spring. What does it mean? What is given on the first sentence?
F equals to 4.9 N.
Okay, good. F, correct. F equal to 4.9 Newton. This one?
S equal to 5.
No. It's not the amount of stretch. Stretch maksudnya regang. Berapa yang dia regang.
Oh, faham.
Yang ni adalah original length of the spring. So yang ni adalah length of the spring. 5 meter. Bukan S. Okay, at equilibrium position, the spring measures 5.98 meters. Dia macam ni. Initially, we have a spring with the length of 5 meters. No object yet at the bottom. After we attach a mass here, the spring, the length of the spring, the total length of the spring will be 5.98 meters. So the amount of stretch is asal spring tu 5 meter. Letak objek, panjang spring dah jadi 5.98 meter. So what is the amount of stretch? Berapa regangan dia? Dia regang sebanyak berapa?
0.98.
Yeah, you are right. 0.98. S is the amount of stretch. So we have to take 5.98 minus 5, which is 0.98. Yeah, we have to really careful while reading the problem. Don't jump to the conclusion. See, 5 meter is the amount of stretch. Read the question carefully. Then you will get the right information given. The surrounding media offers a resistance. Resistance is a damping force, which is equal to the instantaneous velocity. Meaning here, beta dx dt is, beta is 1, dx dt. Normally we put 3 times the instantaneous velocity. Here there is no such 3 or 2 in front of instantaneous velocity. So meaning the damping force is 1. The damping constant is 1. Beta is 1. Beta is 1. So we get damping force is dx dt. See the condition given. The mass is released from rest. From rest meaning not moving. Static. So the velocity at time 0 is 0. That's why I get here. And x of 0 is the displacement of object at time t, 0. Is 2 meter above. So we put it minus 2 meter. Calculate the value of m. We don't have the mass yet. So we use mg equal to ks. Use m 9.8. S is F is 4.9. So we get M 0.5 kilogram. Then substitute in the differential equation. We use F of t equal to 0 because of no external force. M equal to 0.5. Damping force, damping constant is 1 times instantaneous velocity. K is 5. Divided by 0.5, we get d square x dt square plus 2 dx dt plus 10x equal to 0. I get the coefficient of d square x to be 1, so divide by 0.5 on both sides. Okay, solve this equation. Here we have to use the quadratic formula because we have b square minus 4ac equal to minus 36, which is less than 0. We will get the complex root. So d equal to minus 2 plus minus square root minus 36 minus square root minus 36. We get square root 36 square root minus 1. So here square root 36 is 6. Square root minus 1 is I. That's why we get minus 2 over 2 here plus minus 6i over 2. That's why we get minus 1 plus minus 3i. So the general solution would be x of t E alpha t C1 cos beta t plus C2 sin beta t. Here alpha is minus 1, beta is 3. Substitute here the value of beta and alpha. Then we get x of t is e to the power of t C1 cos 3t plus C2 sin 3t. Okay, next is to find C1 and C2. Same as the problem before, we will use the initial conditions given to find the constant C1 and C2. X of 0 equal to minus 2, we can apply t equal to 0 directly in the equation. X of 0, t0, here 0, 3 times 0, 3 times 0. So we get sine 0, 0. Cos 0 is 1. So x of 0 is minus 2. Substitute minus 2 here. So solve for C1. For the next part is to find x prime of t first before substituting t equal to 0. Differentiate x of t. We have to use product rule of differentiation. We get this equation. Substitute t0. Finally, we get C2 is 3 over 2. 2 over 3, sorry. 2 over 3. Okay, the type of motion is under damped free motion. If we sketch the graph, or you may use any software to sketch the graph, we will have this shape. They will be up and down and gradually will stop at equilibrium position. Okay, that's all for today. We only discuss on 2 types of motion. Free undamped motion, which is also known as simple harmonic motion, and free damped motion. Three types of free damped motion: under damped motion, critically damped motion, and finally over damped motion. All the differential equations are of the type of mx double prime plus beta x prime plus kx equal to 0, which is homogeneous differential equation. And then we have one more left, which is systems with with external force or driven motion. We will continue the discussion on the last topic in classroom face-to-face. So before I end the meeting, any question related to the problem being discussed? Okay, if there is no questions, I will end up the session this afternoon. Good luck and try to practice a lot of exercises from our manual or any
Okay, thank you for your patience and your commitment during the online class. See you again and Assalamualaikum warahmatullahi. Bye.
Thank you, Madam.
Madam.
Thank you, madam.
Thank
you, madam.
Okay. Tak ingat sebab selalunya kan dia sambung.